So first things first, as always, got to share out the little stream. If you do join in, please say hello, and let me know if you can hear me. So I need to customize my channel apparently. I'll do that later. So go to the Twitters. Okay, apparently it says I'm live. Beautiful. Going live on Twitch. Cleaning up TensorFlow notebook code ready for video recording. Ready for recording new course videos. Come and say hi. Come dance, party, and say hi. Of course, going live on Twitch, cleaning up TensorFlow notebook code, ready for recording new course videos. Yes, yes, yes. That will do. So this is going to be an experiment, as all things are. Today's going to be an experiment. Can I write understandable words whilst live streaming? Maybe, maybe not. We will find out. Yo, French Toast Mafia, Alex. What's going on, my friend? It's Alex, right? I remember that from yesterday rather than reading out French Toast Mafia. My brain just had to click over. Today, my friend, we are cleaning up notebook number 7. So we need to make sure that we have a GPU available, NVIDIA SMI. Yesterday we made sure all of the code in this notebook runs head to tail. That's a big tick. And today I need to reorder this so I can record it. So clean up headings. That's what I'm going to do. I'm going to go in this order. Clean up model loading code. Yes. We've done that. We've used mixed precision training. So I'll put some green emojis to where we got. Upload trained models to Google Storage. We've done that. Make sure mixed precision works with a local model. Yes, we have done that. Okay. So clean up headings. That's the first thing I need to do. So check GPU. How about we... Thank you for letting me know that you can hear me, by the way. I appreciate that. It's kind of, I always find it strange when I'm like listening to myself talk live. I can watch myself when I'm editing videos, but talking live is strange because it confuses my brain. Check GPU. Let's go through our headings. Check GPU, I think that's a good order. Do we have a Tesla T4? Yes, we do. We might as well get our data ready, because that takes a few minutes. So I'm going to load and download the data. If you're joining this stream, this is what we're doing. I'll put that over there so you can see. But now we have to clean up our notebook. So I want to let you in behind the scenes of, I am preparing materials for the TensorFlow course here, TensorFlow Deep Learning. And so I've done this same process for all of the other notebooks here. I've basically written the notebook myself and then gone back through it and added text explanations to it. So it's like reading documentation with code or something like that. Now we're up to 0.7. We've introduced a couple of new things in here. The main one being faster data loading, as well as mixed precision training. And I'm going to make this milestone project kind of like an outline. So rather than in the other ones, I've written all of the code and students follow along with that. This one I'm going to have 2 versions of the notebook. One is going to be with all the code that you've seen that we've written here, if you've tuned into past live streams. If not, by the way, you can see past live streams at this channel. Q archive. I'm going to put that there. All past live streams are here. So that's the channel. It's called Daniel Burke Archive. Ashik, what's going on, my brother? Oh, look at that. You've got a sword next to your name now. Look at that. Can you see that? You got a sword. Moderator. My boy. Okay, and I forgot. I also have to share it in the Discord. Going live on Twitch. So yeah, that's what we're doing for this notebook, is we're cleaning it up and making it like the other ones here so that we can use it as a reference. And then I got to go to ML Data Science. Boom. Oh. Okay. That is done. And hello, Sleepy One. That's a cool name. And hello, Yogesh. Good morning, my friend. Thanks for the sword. Yeah, I don't know what... I still haven't worked out what logos Twitch give. We've got a Tesla T4. That's what we want. Now let's start jumping through these headings. Make sure they're correct. Get helper functions. Yes, we want the helper functions. Download data. Yes, we want to do that. However, this can go in here. I want to really make this notebook nice and fresh by the end of today, because right now it's a mess. There's TKs everywhere. Probably going to stream for... This is going to be a little bit of a challenge. I want to see if I can write. I've seen that I could code live, but I want to see if I can write explanations and stuff live. TK, exploring, TensorFlow 101, data from TensorFlow datasets, yes. TK, plot an image, yes, just to make sure. Visualize, visualize, visualize. What's the Data Explorer's motto? Visualize, visualize, visualize. Boom, boom. And turn image and label tensors into batches for fitting. Yes, that's correct. I need some pre-processing functions. So, how about I change this one to create pre-processing functions for our data. And then batch and prepare data sets. Yes, this is a big part of it. This little section here. Creating modeling callbacks. Already have the TensorBoard callback. Since we're going to be training a fairly large amount of data, create modeling callbacks. Yes, I'm going to change this to do. TK. This can be now set up. Mixed precision training. Build and fit feature extraction model. Build and fit feature extraction model, yes. Check the layers in our model for check which layers are in our model are trainable. Check which layers in our model are trainable, not trainable, and what is their D-type policy. We'll do the base model as well. I might make another heading here. Yeah, that's a good idea. Break it down. This is what I've found. Fit a feature extraction model to the TensorFlow datasets. No, to the... I'll just call it fit the feature. Build feature extraction model. This is what I've learned. When you're teaching a quite an advanced concept, you'll really help yourself if you break it down into small little Lego blocks. and teach one block at a time and then combine all of those blocks. Load and evaluate checkpoint weights. Yes. Do we need to do that actually? Why do we checkpoint? I might put this up here. No, we need to create this when we create modeling callbacks. TK, why do we checkpoint? Load and evaluate, save and fit the whole model, save the whole model to file. You can save the model to Google Drive directly from Colab if you wish. See cell below. Fine tuning. Fine tuning all of the layers in our base model. Fine tuning. Beautiful. Mixed precision. TK, note, if you didn't use mixed precision, your model fine-tuning probably takes up to 2.5 to 3x longer per epoch. See below. Okay, we're in a good place here. To do download fine-tuned. Here's something we prepared earlier. It's like a cooking show with machine learning, right? Otherwise, you're going to be waiting forever. Oh, by the way, we've got a new rule for this stream. New rule for this stream. New rule. ML fit. 1 epoch equals 5 push-ups. Squats okay. So this is the rule for this stream. If you're watching, I'm going to be doing it as well. ML fit. If we train a model for 1 epoch, that means we have to do 5 push-ups or 5 squats. So 5 epochs, 25 push-ups or 25 squats. Make sense? Okay, let's go back to the top and start from where we were before. The data set is downloaded. Yes, it is. Now we're going to just, okay, so the headings are quite correct. Let's start burning through from what we need to do. So I'm going to put up here as well. TK. I need intro, how you, TK intro, TK what we're going to cover, TK how you should approach this notebook. So I'm going to do those later, but now I'm going to go through each of the parts and start to take care of all of these headings here. We'll see how far we can get. Thank you, Ashik. Oh, you're working on Zoom movements and wake up stretch? That's awesome, my man. That's awesome. You just opened Google Drive on my phone via Google Assistant. My bad, Puba GB. Abhijit, enjoy those past streams. I'll try and upload streams basically the same day that they're done. And I'll go to that YouTube channel. I'm not going to edit them at all. They're just going to be exactly as if you were watching it live. Check GPU, because otherwise I've got too much shit on. So, check GPU. For this notebook, we're going to be doing something different. We're going to be using mixed precision training. Mixed precision training was introduced in TensorFlow 2.4.0. Very new at the time of writing. A very new feature. What does mixed precision training do? Good question. What does mixed precision training do? I want to not just repeat what comes straight from the documentation. So this is what I do when I try to write these descriptions, is I try to describe it in my own words how I understand it, and then link references for if people want to understand more. Because the way I've kind of learned things, or the way I kind of learn things, is people will automatically start to research more about things that will interest them. So rather than you reinventing the wheel of the exact definition how things should be explained, as long as you're not bullshitting with your explanation and just making things up, I've had hands-on for the past however many streams we've done, 5 or 6 or whatever, or a few weeks, hands-on experience with mixed precision training. So this is how I understand it. What does mixed precision training do? Mixed precision training uses a combination of floating point 32, uses a combination of full precision, float 32, and half precision, float 16. What could you call it? Is it data storage? And half precision. Let's go into the mixed precision. I need to figure out what I should call this. Floating point types. There we go. A full precision. Is full precision precision? Here we go. Full precision. Single precision. Single precision and half precision data types to speed up model training. What does mixed precision Does that make sense? During training to make it run faster and use less memory. To speed up model training. We'll talk about this more later on. But in the meantime, you can read the TensorFlow documentation on mixed precision for more details. We'll talk about this more later on, but in the meantime, you can read the TensorFlow documentation on mixed precision for more details. Okay, beautiful. And then for now, add a little link here. And now we got to go, wait, where did that go? Oh, we don't want that. We want this here. For now, we need to make sure, since we're starting up a new Google Colab, for now, actually, yeah, for now, before we can move forward, if we want to use mixed precision training, we need to make sure the GPU powering our Google Colab instance, if you're using Google Colab, is compatible. For mixed precision training to work, here we go. I'm just going to put that there. You need access to a Tesla on Google Colab. No, for mixed precision training to work, you need access to a GPU with a compute score of 7+, with a compute capability score on 7+. However, offers P100 K80s and T4 GPUs. Google Colab offers P100 K80, however, therefore, before we proceed, we need to make sure we have access to our Tesla T4 GPU. In our Google Colab instance. If you're not using Google Colab, you can still you can find a list of various NVIDIA GPU compute capabilities on NVIDIA's developer website. Beautiful. Does this make sense? Various NVIDIA GPU compare. How do you even spell NVIDIA? Is that right for NVIDIA, or is it all capitals? NVIDIA. Yeah. NVIDIA. It's actually a really cool name, isn't it? NVIDIA. And then I'm going to put a note here. Note. This should output Tesla T4. Otherwise, if using Google Colab, this should output Tesla T4. Otherwise, you won't be able to use mixed precision training. NVIDIA SMI, and I think you might be able to just go L. Yes, Tesla T4. There we go. Oh, beautiful. I'm going to can that. Bring that down here. resource. Does this make sense? For this notebook, we're going to be doing something different. We're going to be using mixed precision training. Mixed precision training was introduced in TensorFlow 2.4.0, a very new feature at the time of writing. What does mixed precision training do? Also, since mixed precision training was introduced in TensorFlow 2.4.0, make sure you've got at least TensorFlow 2.4.0 plus. Import TensorFlow check TensorFlow version as TF, and then print TF version. Google Colab, I believe, has all of the latest versions of TensorFlow. There we go. Okay. Should be 2.4.0 plus. So if we go here, TensorFlow 2.4.0 blog. What's new in TensorFlow 2.4? Yeah, so this is the newest, one of the newest features in TensorFlow. December 14, 2020. So only 2 months ago was this feature even available on TensorFlow. It was experimental before this post. Here we go. TF 2.4 is here with increased support for distributed training and mixed precision. Wonderful. Updates and Keras. In TensorFlow 2.4, the Keras mixed precision API is moved out of experimental and is now a stable API. There we go. Let's move this in here. Up to 3x on modern GPUs. And I'm going to put this link here. There we go. Okay, so that one's done. For me, we read back through it. For this notebook, we're going to be doing something different. We're going to be using mixed precision training. Mixed precision training was introduced in TensorFlow 2.4, a very new feature at the time of writing. What does mixed precision training do? Mixed precision training uses a combination of single precision float 32 and half precision data types to speed up model training, up to 3x on model GPUs. We'll talk about this more later on, but in the meantime, you can read the TensorFlow documentation on mixed precision for more details. For now, before we can move forward, if we want to use mixed precision training, we need to make sure the GPU powering our Google Colab instance, if you're using Google Colab, is compatible. For mixed precision training to work, you need access to a GPU with a compute capability score of 7.0 plus. Google Colab offers P100, K80, and T4 GPUs. However, the P100 and K80 aren't compatible with mixed precision training. Therefore, before we proceed, we need to make sure we have access to a Tesla D4 GPU in our Google Colab instance. If you're not using Google Colab, you can find a list of various NVIDIA GPU compute capabilities on NVIDIA's developer website. If you run the cell below and see P100 or K80, try going to Runtime Factory Reset Runtime. Note, this will remove any saved variables and data from your Colab instance and retry to get a T4. Boom! That is some good writing there. Let's get rid of that TK, because that can be wonderful. That can be a section. How's the chat going? Oh my goodness. Did you start learning TensorFlow when? I did a bunch in the TensorFlow 1 days, but mostly with TensorFlow 2. So TensorFlow 2, I think, has been out for almost 18 months, maybe 2 years now, nearly. Rohan, hi and bye, my friend. Enjoy, have a fun day at school. Don't worry, you can watch the past live streams. Ashik has the link to the channel, Rohan. I think I'll send you that on Discord. Abhijit says, really appreciate the work, following your learning path. How I'd start learning machine learning again. That is awesome, my friend. So glad to hear that you're you've added your own changes and you're writing blogs. That's a good way. That's how I've learned a lot. Writing online is one of the best things you can ever do because it puts your work out there and allows other people to find you. Now we're on to the next one. Get helper functions. Now, this is where I'm going to cheat a little because I believe I've used this helper function file. By the way, if we have a look at what this looks like on GitHub, it's just a Python script of a whole bunch of different functions that we use throughout the course. So rather than rewrite them in the notebook, we just import this helper functions.py script. So see here, there's one here, def, load and prep image, yada, yada, yada. Create TensorBoard callback. We can just import the functions from this file. So if we come back to here, if we go into 06, scaling up, I think I wrote some copy here. And what I mean by copy is text. Text about what we've worked on. Here's a beautiful notebook. Who wrote this? I did. Boom. I'm going to just copy this. Create a series of helper functions throughout the previous notebooks. Instead of rewriting them, tedious, we'll import the helper functions.py file from the GitHub repo. Get helper functions throughout the previous notebooks in the course. Instead of rewriting them, wonderful. Get helper functions. We'll download that. I think we already have that. That's all right. We'll pretend like we've just done it. Okay, here's the next main one. This is a new part we haven't used before. Since it's in a compressed format, okay, let's write this. In previous notebooks, we've downloaded our food images from Google storage. However, there's another way to get datasets ready to use with TensorFlow. Oh, is that a... and this is a typical workflow you'd use if you're working on your own datasets. However, there's another way to get datasets ready to use with TensorFlow. For many of the most... I need to write here, food vision... from Food 101 dataset. I'll need to write up here building food vision. An image classification model trained on Food 101 data with better results than the deep food paper. Now I need access to the deep food paper. There we go. Oh, there we go. Oh, it's already there. Okay. We want to beating Food Vision Mini from the previous notebook. Food Vision Mini equals model trained on 10% of data with 101 classes. Food Vision equals Food Vision large. No, Food Vision big equals model trained on 100% of data with 101 classes. Okay, we're building Food Vision big in this one. For many of the most popular data sets in the machine learning world, often referred to as benchmarks, you can access them through TensorFlow datasets. Through TensorFlow datasets. Wonderful. Food 101. I want to actually now, what is TensorFlow datasets? Let's have a look in here. How would we describe this in a sentence? Well, that makes a lot of sense. TFDS provides a collection of ready-to-use datasets for use with TensorFlow JAX and other machine learning frameworks. Through TensorFlow datasets, TFDS. Oh, you guys are asking what the next video is about, the 10-hour video? Ashik, you probably already have access to it. That's a hint. That is a hint, my friend. Can't I keep some surprises these days? Many of the most popular datasets you can often referred to and used as benchmarks. What is TensorFlow datasets? So what is TensorFlow datasets? A place for prepared and ready to use machine learning datasets. Why use TensorFlow datasets? And I've got it over here. Practice on well-established datasets. On well-established datasets, well-established, experiment with different data loading techniques like we're going to use in this notebook. Could you call it that? Did they call it that? Ready to use machine learning datasets. To begin using TensorFlow datasets, we can import it under the alias TFDS. Get TensorFlow datasets. Wonderful. To find all of the available datasets in TensorFlow datasets, you can use the list builders method. We can check to see one we're after. After doing so, get all available datasets in TensorFlow datasets. Yes, that'll do. I'm going to keep it as a surprise. It should be out this weekend as long as I have enough time to edit it all and put it together. Okay, so that's what we want. Beautiful. Beautiful. Looks like the data set where after is available. Note, there are plenty more available, but we're focused on Food 101. To get access to the Food 101 dataset from we can use the load method. In particular, we'll have to tf_ds.load. In particular, we'll have to pass it a few parameters to let it know what we're after. Load, tf_ds load. So the documentation on TensorFlow tf_ds is quite poor, but with a lot of hacking, you can get around it and figure out what you need. Here we go, load. Name string. Calling this function might potentially trigger the download of hundreds of gigabytes to disk. Refer to the download argument. Whether to call build before calling to let it know what we're after. I'm going to put a note here. Note, calling the tf_ds load method will start to download a target dataset to disk. This dataset could be if download equals true, parameter is set. Default. This dataset could be $100 GB plus, so make sure you have space or name name is a string. The target data set, e.g. food 101. Is that how I would do it? Let's get it over this over here and this over here. This notebook is going to look so beautiful by the end. Hope you're all taking note of how filthy this notebook is right now, because by the end it's going to look beautiful. So I need to fill out these: name, string, the target data set. What else do we need? Need split, need shuffle files, I need, what else? As supervised, and I need with info. All right, I'm going to the bathroom to pee, and I'm going to get a drink, and I'll be back in a minute. I'll write this here. Be right back. Bathroom. Okay, I'm back. Who's ready to write some more text annotations for this beautiful notebook? In particular, we'll have to pass a few parameters to let it know what we're after. Split. Split can be, which is, it comes in the form of a list, but list, optional. So the split parameter is quite tricky. See the documentation for more. E.g., train validation. Shuffle files, this is a bool. This can be whether or not to shuffle the files on download. Is that what it really does? Shuffle? Whether to shuffle the input files defaults to false. Defaults to false. As supervised. Bool. We'll have dictionary. Download data in tuple format or true, or download data samples in tuple format. This can be what was it? Input data label or dictionary format. True. I'll put this here. True to or false for dictionary format. With info, this is a bool. True to download metadata. To download dataset metadata. Labels, number of samples, etc. What does that look like? Go back bathroom. Let's see it in action. Method. Wonderful. Include dataset metadata. If so, tfds.load returns tuple data ds info. Shuffle files on download. What splits of data should we get? Note, not all datasets have train valid test. Okay. Target dataset to get from TensorFlow datasets. I think that's pretty good. Don't you? Rather than just reinvent all of the documentation, does that work if I run that? It does. It takes about 5 to 6 minutes in Google Colab. Okay. Now let's write a little progress update here. Wonderful. After a few minutes of downloading, we've now got access to the entire Food 101 dataset in Tensor format, ready for modeling. Now, let's get a little information from our dataset, starting with the class names. Ready for modeling. What is TensorFlow datasets? Why use TensorFlow datasets? Why not use TensorFlow datasets? The datasets are static, might not be suited for your particular problem, but great for experimenting. Okay, that sounds good to me. Getting class names from a TensorFlow requires downloading the dataset info parameter. Downloading the dataset info, is parameter the right word? Variable. Using the as supervised true parameter in the TF load method. Note, this will only work for supervised datasets in TFDS. Get class names. We can access the class names of a particular data set using the, what does features look like? ds_info.features. Features of Food 101 TensorFlow dataset. Using the dataset info.features attribute. And accessing the label key. And accessing the names attribute of attribute. Beautiful. There we go. Lazy is playing. Hello, mate. How are you, my friend? Thank you for joining into the stream. Probably, you've probably been here. That message is probably a few minutes old now because I've been too deep in concentrating. But happy to have you here if you're still here. Exploring the Food 101 data from TensorFlow. Now we've downloaded the Food 101 data set from TensorFlow datasets. How about we do what any good data explorer should? In other words, visualize, visualize, visualize. Let's find out a few details about our data set. The shape, what else? Yeah, we want the shape of our input data, image tensors, the data type of our input data, yeah, that's it, input data, what the labels of our input data look like, e.g. one hot encoded versus label encoded. And what else do we want? We want, do the labels match up with the class names? Oh, we have one here. Because it's multi-level string image shape, but that's pretty self-explanatory, right? What does train data look like right now? Options data set, none 3. To do so, let's take one sample off the training data using the take method. TensorFlow take, or is Python? It's actually Python is take, isn't it? NumPy take? Oh, it might be TensorFlow take. DS take. 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 Beautiful. Copy that. Using the take method. And explore it. Train 1. Train 1 sample. I'm going to call that train 1 sample. Train 1 sample. What does one sample of our training data look like? Because we used was it as supervised? We want 2 tuple. Yes, a tuple. Because we used the as supervised equals true parameter in our TFDS load method above, data samples come in tuple in the tuple format structure. Data label. Let's loop through train one sample. I might sound like a little bit of a crazy guy, but I'm just basically narrating what I'm doing because this is what I want to, this is how I make these sort of notebooks, right? I type what I speak because I imagine how do I want to run this like lecture if I was, or record the video. And so I write words as if I was speaking it out loud, if I was teaching someone, if they were sitting beside me. That's how I try to write this. Let's loop through our single training sample and get some info from or in our case, image tensor label. And get some info from the image tensor and label. TensorForm, image label, TensorForm, image target. Target class. From food. Hey, train one sample is available. How is that not available? Didn't I just, oh, I changed it later. Holy crap, I drank a lot of fluid while I'm writing. Image shape, D-type uint 8, food 101, TensorForm 23. Churros, beautiful. Now if I ran this again, does it give me the same one? Yeah. No, it gives me a different one. Running the cell above a few times will give a different result each time. Because we set the shuffle, what was it, shuffle files? Files equals true parameter in our we give a different result each time. Ashik, you're exactly right. That's how I want it to be. I want it to be as if you were sitting next to... I want people to watch my coding videos and educational videos. The live stream's a little bit different because it's I'm making the materials at the moment. But when I formally record them, I want it to be like you're partner coding, basically. You're coding side by side. That's a really good way to learn. Okay. All right. Looks like our image tensors are in... what could I say this? Have values of... So image... That's right, we need TF reduce min. All right, it looks like our image tensors have values of between 0 and 1 and 255, standard red, green, blue color values, and the values are of data type uint8. We might have to pre-process these before passing them to a neural network, but we'll handle this later. In the meantime, let's see if we can plot an image sample. Beautiful. Okay, so we're slowly working towards taking care of the headings here. Have we finished this? Not yet. I'll go back through and read it all later. So, plot an image from TensorFlow datasets. That is amazing, Ashik. So glad to hear that. That's what I want it to be, right? I wanted you to come away from the course having written lots and lots of code. We've seen our image tensors in tensor format. Now let's really adhere to our motto. Let's plot one of the image samples using matplotlib's imshow and set the title to the target class name. Imshow, matplotlib imshow. We could just do matplotlib.pyplot. What are we going to get? Delish grilled salmon. Now, if we go again, no, it doesn't call a new one. Delicious. Now let's pre-process and get it ready for use with a neural network. Create pre-processing functions. What did we use? What's it called? Image dataset from what's it return? TF dataset object. Now let's see what we can do here. Create pre-processing functions for our data. That looks much better, doesn't it? So that's what we need to do. So we need to pre-process image. Pre-process a single sample image and check the outputs. Create our data, all different size tensors, models like float32 data, scaled data, So I need the order here. Map, shuffle, batch, prefetch, cache. Beautiful. So this would probably be the main one. So these two are some of the main information about this whole notebook. Preprocess image. Converts image data type. When our images were in folder format, we used whereas models prefer data to be models like data to be float 32 all tensors have the same shape, e.g. 224, 224, 3. Beautiful. More specifically, our data is currently in uint data type, comprised of all different size tensors, different size images, Not scaled, the pixel values are between 0 and 255, whereas models like data to be in float 32 data type have all of the same size tensors. Batches require all tensors have the same shape, e.g. 224, 2243, scaled, values between 0 and 1. Okay. In note, pre-trained what we're going to be using. Dot efficient net. TF Keras layers. Rescaling, is it still experimental? Yes, it is. That is all right. Note, pre-trained EfficientNet models, BX models in TF Keras applications EfficientNet, what we're going to be using have rescaling built in, but for many other model architectures, you'll want to rescale your data, e.g. get its values between 0 and 1. Okay, that'll do. To take care of these, we'll create a pre-process image function which resizes an input image to a specified size, as well as converts its current data type to TF float 32. Which resizing it to a specified size and converts an input image tensor's current data type, resizes an input image tensor to a specified size using TF image resize using TF cast. Wonderful. TF image resize. TF cast. Bringing it all together. Make a function for pre-processing images. as input, even though it does nothing to the label, is currently in the tuple structure. Let's try our function out on a target image. Excellent. Actually, maybe I'll put the data type here as well. Yeah, that's a good idea. Data type equals image.dtype. Copy that. Beautiful. Looks like our image function is working as expected. Image, input image gets converted from uint8 to float32, and gets reshaped from its current shape to Was that line too long? Boom. All this food visualization is making me hungry. How about we start preparing to model it? Yeah, that's what we have to do. Okay, so now we have a pre-processing function. And right now, what's our data set in? Train data, test data. What's it look like? Options data set. Let's go here. TensorFlow options data set. You're right, Ashik. Using TensorFlow datasets and load them by just filling the available arguments is when we get data from elsewhere. So in the previous 3 notebooks, we get data from elsewhere. So in this, and this, actually all of them, we get data from elsewhere and use TensorFlow methods to pre-process it. Food Vision Milestone Project 1 is where we're just exploring TensorFlow datasets so that we can practice using another part of TensorFlow. But otherwise, you will often have your data set here or working from Google storage or something like that. And you can use very similar functions to what we're using now to load in your data set. So if you converted your data into tensors from, say, folders of images, you could still do this sort of process. Options dataset. No, you're right. So in the previous notebooks, Food 101, oh, this is TensorFlow datasets. Hey, what's happening with TensorFlow? They just had a Food 101. RSVP for your local TensorFlow Everywhere event today. Find an event. Is there one near me? I wonder. Food 101. Yeah, so in a previous notebook, we've just downloaded this. The Food 101 dataset from Kaggle, which is actually originally from Food 101 Data Vision. This one. So we turn this into the standard image processing format. So you can download it right from there. Food 101. But we've also got a notebook on the TensorFlow course of pre-processing the images. So image data modification, you'll see this as you go through the course. So sorting out images from Food 101 dataset. Notebook to sort out the images in the Food 101 dataset into computer vision data layout. For example of the file structure. Top level folder, pizza steak, train, and then you sort the images out by class, and then test, and you sort the images out by class. So to replicate this notebook, you need the data download from each of the following. And then I've just gone through and written code here to pre-process data into the format that we want. But you can see that. This just pre-processes data. But very important point. However, that's going to be different for almost every data set that you work with. But that's one example of turning the image data set from Food 101 into the standard computer vision practice of separating your data in train and test files via class names. Where were we before? TensorFlow Everywhere. Oh, there's only one in Melbourne. Oh no. TFUG Sydney. What's TFUG? Sydney, 12th of March. Wow. That's cool. What's happening here? TensorFlow Everywhere. Superpowers for next-gen web apps. Oh, TensorFlow JS. When is Google's next summer of code? I need to get rid of some tabs here. Your brain is as good as computing as you have tabs open. The little less tabs you open, the more space for your brain to compute. Let's get rid of all these tabs, hey? Good. Oh, today, March 10. Holy crap, that's today. March 10. Now you can apply. This is very cool. I'll be back. Siobhan's, I think there is interstate travel in Australia right now. My mate came up from Sydney the other day. Alex, a line of TensorFlow a day keeps the doctor away. I like that one. Krishna, good noon. Good to see you. When is the next developer summit? I don't know. Let's have a look. TensorFlow Developer Summit 2021. Dev Summit. Oh, I would say it might be soon. 2020? March 11, 2020. What is TensorFlow saying? I think they might have replaced it with TensorFlow Everywhere. Okay. What organizations are available for Google Summer with Code? Oh, Anki, Blender, Chrome web browser, Dart, that's a programming language, Django, Git. Oh, what is Git? That's really cool. GitLab. Genome. Healthcare for Humanity. Oh, IT health. Oh, MediaPipe. I like MediaPipe. This is Google of summer of code, by the way. Postgres. Python. Hey. Okay, when we get to the bottom of this, we're going back to writing more code. TensorFlow. They're using the old logo, but what do they want here for media pipe? Media pipe is really cool. Built-in fast ML inference and pre-processing, processing accelerated even on common hardware. Explore what is possible with media pipe. Human pose detection and tracking, high fidelity human body pose tracking. Hand tracking. Object detection and tracking detection of tracking objects in a single video pipeline. Media pipe. iOS solutions. This is really cool. What could you build with this? Solutions. Face mesh. Human pose detection tracking. Hand tracking. All right, how do I use this for iOS? Can I use this with Swift? Set Python 3.7. Maybe that could be a future stream. Go through that. A simple camera app for real-time Sobel edge detection. Oh, hello. MediaPipe users provides Objective-C bindings for iOS. Oof. Okay, getting distracted. Back to writing information here. While this food visualization is making me hungry, how about we start preparing to model it? Do we need this up? Let's go back to what we're doing today. Ashik, I'm not taking part in Summer of Code. I'll be doing my own Summer of Code. Well, it's already past summer for me, but I'm going to be doing my own. After the course is finished, that's my main focus. After the course is finished, I'm going to be working on a fairly extensive project. I want to see where it goes. So that's why we have to finish all of this. Okay, batch and prepare data sets. Right now, our data, that's what we were trying to figure out. What is an options data set? TensorFlow options data set. Why isn't that showing up? Before we can model our data, I have to turn it into batches. Why? Because computing on batches is is memory efficient. We turn our data from 101 plus 1,000 images, 101,000 image tensors, and this is train and test combined, into batches of 32 image and label pairs. Image tensors and labels. Thus enabling it to fit into the memory of our GPU. Now, what do we have to do here? To do this in the most effective way possible, I'm going to be leveraging a number of, let's look up the performance guide again. Number of methods. Number of methods from the tf.data API in the most performant I'm going to put a resource in here. No, this emoji. Resource for loading data in. To do this in an efficient way. In an effective way. For loading data in the most performant way possible, see the TensorFlow documentation on better performance with the TF data API. Beautiful. This is what we want. We need to kind of, because all of this stuff is in my head right now, right? And so that's why I need to kind of reverse engineer what I've already done in my head to explain it. So we need some foundations, some information, some backstory to this. Specifically, we're going to be using dot. Here we go. Boom, 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 boom. We're going to be using map. Maps are predefined. Now, do we have map? Map. Yeah, which applies a user-defined function to each element of the input data set. To make this possible, similarly to the prefetch and interleave transformations, map transformation provides map for methods with the How about this? An idea. Autocorrect for Google Colab. Setting it to wonderful. Maps a predefined function to a target dataset, e.g. pre-process image to our image tensors. Is shuffle in here? Shuffle. Do we need repeat? Default behavior is for the dataset to be repeated infinitely. Okay, so I don't think we need repeat. Is repeat here? It's not. Okay, we don't need repeat, but we do need batch. Wonderful. Randomly shuffles the elements of this dataset. The dataset fills a buffer with buffer size elements, then randomly samples elements from this buffer, replacing the selected elements with new elements. For perfect shuffling, a buffer size greater than or equal to the full size of the dataset is required. For instance, if your dataset contains 10,000 elements but buffer size is set to 1,000, then shuffle will initially select a random element only from the first 1,000 elements in the buffer. Once an element is selected, its space in the buffer is replaced by the next. Defaults to true. Beautiful. So shuffle randomly shuffles the elements of a target dataset up to parameter buffer size. Ideally, the buffer size is equal to the size of the dataset. However, this may have implications on memory. Because if we go to performance and we look up shuffle, yeah. So shuffle maintain an internal buffer of elements. If there's too many in there, it may not be performance. Batch. Let's go to batch. We want to shuffle then batch. Yes, that's what we want to do. Turns elements target data set into batches. Size defined by parameter. Batch size. So we want to go data, map, a function, shuffle the data, batch the data, prefetch the data. Create a data set that prefetches elements from this data set. Most dataset input pipelines should end with a call to prefetch. There we go. This allows later elements to be prepared while the current element is being processed. This often improves latency and throughput at the cost of using additional memory to store prefetched elements. Damn it. Map function. call shuffle after cache. Okay. Did we see prefetch? Prepares subsequent batches of data whilst other batches of data are being computed on. Significantly speeds up. Improves data loading speed but costs memory. Cache caches all elements in a target dataset saving loading time. Will only work if your data is small enough to fit in memory, or if you have lots Okay. Some things to note. TF data auto tune. What does this do? Things to note, can't batch tensors of hence pre-process hence our pre-process image function. All right, I think this is taking shape. I think that we can go down to okay, let's read through this. See if we're covering the bases we need to cover. Basic mechanics. How long have we been streaming for? Oh, wow. Just over 2 hours. See, this is a very... not much action in today's stream. Batching. There we go. Shuffle. Pre-processing data. There's our map function. Beautiful. Beautiful. Okay, so we're covering a fair bit of content here, so this is great. Let's get out of these. All right, we're going to Whoa. Above is a lot, but once we've coded it below, it'll start to make sense. We're going to go through things in the following order. Original dataset, e.g. train data, map, shuffle, batch, prefetch. This is like saying, hey, map this pre-processing function across our training data set, then shuffle a number of elements before batching them together and prefetching and preparing new batches whilst the current batch is before batching them together and prepare make sure you prepare new batches, prefetch, whilst the current batch is being whilst the model is looking through the current batch. TK image of loading data, steps above. And now let's check out what our Where'd my key emoji go? I want my key emoji, man. Significantly? What did TensorFlow Datasets say about prefetch? Just going to write exactly what the documentation says. Now I think I'm up to here. How far have we gotten through this? Creating model callbacks. So we've gone through check GPU, check helper functions, we've gone through that. Okay, creating model callbacks. Onward. Since we're going to be training on a large amount of data, note, we've created this callback earlier, callback before, and have imported it from helper functions .py as why did that come up as code? We don't want that as code. We don't need that as code. So we can also start fine-tuning. Checkpoint saves our model's progress at various intervals so we can load it and reuse it later without having to retrain it. Checkpoint is also helpful so we can start fine-tuning our model at a particular epoch. So we can start fine-tuning so that we can and revert back to a previous state if fine-tuning offers no benefits. Beautiful. Okay, we've been going for about 2.5 hours now. So I think I'm going to finish off the rest of this later. I'm going to go take a break because I've been typing and my brain is hurting. Well, not really hurting, but I've just I think I've written a fair bit. I mean, before this, we had none of all of this. So clean up headings. Yes, we have done that. Add text to different sections. Where's my green tick emoji? It's not loading. Clean up headings. No, I just want the green tick. Clean up data loading. Yes. So this is what we're up to. Okay. I'm up to here. Up to here. Set up mixed precision training. I'm going to go back through and do some more reading on mixed precision training so I understand that. So tomorrow when I come back and start writing it, I've got all the stuff stored in my brain. And then we'll finish off the rest of this. But I'm going to save this to update it in the GitHub. Save a copy in GitHub. So if you want to, and you want to have a look at this, read through the first few sections that we've updated today. Update a bunch of annotation text. Getting closer to still a bit more to go. C to do. Okay, I think that is it. TensorFlow deep learning, main, yes. So not very much action on this stream, but we were present. Let's just go in here. GitHub, see if it got updated. 11 seconds ago, there we go. And this is a cool thing. We can actually check how much we did. Let's go in there and we go CD TensorFlow on it. CD desktop, CD TensorFlow course, CD TensorFlow ls, git status. Have I added anything there? Nope. So if we go git pull, because I just saved, this is my local directory of everything that's on GitHub. Because I just saved what's here in the changes that we made into GitHub, if I go git pull, it's going to pull all of those new things and we can see how much changed. Git pull, look at that. One file changed, 07 Food Vision Milestone Project. We did 580 insertions and 322 deletions. So a lot in total. So we added a whole bunch of different lines. That's pretty good, 580 insertions, 580 lines of insertions, but we also removed a lot of crap. So tomorrow, we're gonna finish that off, and then we'll get closer and closer to recording. So I'm going to update the README as well. README. I've loved this little log as well. So we go here, 10 March. Typed a whole bunch of explanations into notebook 07. Continuing tomorrow. And this is the status as of, so I want to try and finish notebook 07 by probably tomorrow, and then record the videos maybe the next day or very early next week, and then section 7 will be done. Then we can move on to 8, 9, and 10. Very exciting. And then I'll git pull these as well. So the README, yeah, just had a couple of changes. Beautiful. But that is going to be the end of the stream. Thank you very much for joining in. We didn't actually train a model today, so we didn't follow our ML fit. But the new rule is 1 epoch equals 5 push-ups. We'll do that tomorrow when we start training models. But clean up headings, yes, we did that. Clean up data loading, we did that. And so write text explanations for different sections. I'm going to move these up here. This is what we'll take down tomorrow. Don't forget, you can see all of these streams are, if you're just tuning in or if you're tuned into the back end, you can go to the archive channel and watch them all there. But anyway, peace out. Keep machine learning, keep moving, keep creating. I'll see you later.